You see, in the last class, okay, you must remember that we talked about the lower limit of mass of a star, and there we talked about the density temperature diagram, equation of state various regimes, and at the very end of the lecture I told you that the upper mass limit will be basically defined. You can calculate that using that transition region between radiation and ideal gas. Now here I have shown you two very different type of techniques, but again there are certain similarities as well to estimate the maximum mass of a star. Just as human beings also have a maximum mass, you cannot have more than 200 or 250 or so kg. There will be so many automatic degenerative functions inside the body that he will have to either lose his weight, he or she, or perish. He will just die. He or she will die. Anyway, the same thing will happen for stars. What happens is that when I am talking about radiation, right? So very massive stars, their radiation will be important. That means photons. So photons generated at the very core of the star, they will be going outward, and as a result, you know, they can generate radiation pressure. They have, right? That is the equation of force for them, photon gas. Now because of, if we have got very large photons and they have got very sufficient energy, mass of the star is large, then this means huge photon contribution. What will happen is that the outer surface, if the mass is very large, so photon pressure will be very large, so much larger than even your gravitational pressure. Then what will happen? The very outer layers, it will just blow away, and that is basically solar wind. Okay, so outer layers of the star will just blow away because of the effect of radiation pressure, and this is what we know as solar wind. Now let us try to estimate it. Here I am presenting the first method. So let me talk about core here. So what is happening in the core is, what is the radiation pressure at the core? I am just writing in terms of temperature. Now why I am talking about core? Because you know the core has got the maximum temperature, right? And the pressure due to radiation, it scales as T to the power 4. So here the pressure due to radiation will be very high. So this is what I have written now. Now what about the ideal gas pressure? Again I have written it here. Okay. Now what I am going to do next is I am going to write the entire pressure at the core as the sum of these two contributions. Fine. And to make matters simple, what I am going to do is, let me define this this very small fraction f. So f is a fraction of gas pressure to total core pressure. Again, gas pressure at the core. If this is so, then the radiation pressure will be just 1 minus f into Pc. Very basic algebra, but it has got very great importance. Okay, so after that, if we use this result over here for gas pressure, then I can write the central temperature in terms of this F and Pc. So here gas pressure is not there, so F and Pc is there. Next, what I am going to do, I am going to use this result in this case, and I am going to use this result as well. So both this as well as this, the two of them together. If I use that, then I will get this relation. Very basic, just a different form of this relation. From there, similarly, just as previously, I wrote down Tc, now I am writing down Pc. That means my entire aim is to write in terms of the central pressure at the core, total pressure. So this is Pc. Fine. Now look at the expression. Here we have got some constants, this is some F, Kb, density. So basically density is here. What about mass? There is no mass dependent. There is nothing mass. But we are out here investigating, trying to find out the upper mass limit. Right. So what will we do? Let us again try to estimate the same pressure using a different technique where there will be some mass. And then we will equate these two terms together. Now I am not going to show you the details of that, but there is a model in literature known as Clayton-Scalar model. Here the central pressure depends on m to the power 2 by 3 and rho c to the power 4 by 3. This is the form. You remember that previously in our previous few classes I have talked about different types of scalar models, and the basic principle was to write density as a function of r. You remember this, right? We wrote this. The most very basic model is just rho r is equal to rho 0. This is constant density model. Next, let me write rho r is equal to rho 0 into 1 minus small r by radius. This is linear density model. If I write like this. Next, rho 0 into 1 minus r square by, this is quadratic density model. This we talked about in the last class. So these are just a very simple density type models. Here I am using a different model, but look, in each of this model, you remember, you can also write, after this, you can also write PC in terms of that. You remember? Similarly, even using the virial theorem also, you can write the central pressure. In the last class we saw those things. So here I am just showing you yet another model. I am introducing you to this. So this is Clayton-Scalar model. Fine. Now let me come to the actual motivation for introducing this. So my motivation is to match the two of them, and this is what I am doing over here. So if I match the two of them, I can write the m total mass as this. Fine. Now you see here, when will the star become unstable? Very large mass, when pressure due to radiation is very high. So this means radiation pressure is greater than gas pressure. So this means, you see, this simple thing, by introducing this f, I can write it as f less than half. And this is where I am introducing the inequality. Okay? So this just means that I will have something like m less than m max. Now I am doing two assumptions. Number one, m average is equal to 0.6 into atomic mass unit, 0.6 U. Number two, let limiting case is f is equal to half. Then what I will get? I will get m is equal to m max, and you can do this calculation yourself and check that m max comes around to be 100 solar masses. So this is more or less a limit. Okay, using this very basic technique and using the Clayton-Scalar model. Next, what we have here is the second method, and this is the Eddington luminosity. Now this luminosity is basically the maximum luminosity that can be carried by radiation inside a star which is in hydrostatic equilibrium. Okay, now of course the same hydrostatic equilibrium concept is there as well, but we have not invoked the principle of hydrostatic equilibrium explicitly. I have not talked about it, but it is there. Otherwise, how can you talk about a constant radius star, right? It is there, remember this. Now what I am going to do next is I am going to invoke this hydrostatic equilibrium condition here. How? You must remember the equation of radiative energy transfer. You see, this is the technique of using Eddington luminosity. So I have to talk about luminosity. Why do you estimate? How do you estimate luminosity? Using the equation of radiative energy transfer. So this is our equation. You can also write in terms of del T del M. Okay? Fine. Now we know the radiation pressure in this form. Again, the same thing, but written in terms of A. Okay? Because of that, you get a pressure gradient, right? So this is the force due to photons, pressure gradient, and this is the form. So Same thing like previous. Now for stability, the force on the photons from the center, this is the force, this must be less than the pressure, inward pressure required for hydrostatic equilibrium, right? So this is the pressure gradient due to hydrostatic equilibrium, and this is due to the photons radiation. So this must be there, otherwise we cannot have stability. Fine. So I am just equating the two of them, and you see what I am getting. I am getting a very simple relation, which is the in terms of luminosity now, not in terms of mass. There is no mass. Of course there is, but it is mass of the proton. This m is mass of the proton. Okay. Now, so I can write L is less than this relation, and this is known as, this is the Eddington luminosity. Right, basically maximum luminosity carried by radiation inside a star which is in hydrostatic equilibrium. Now there is something very important, which is that this, you can say this is a mass of proton, or also, but in this particular derivation you cannot say this is a mass of a proton. This is basically mass at radius r. Right, but there are other type of derivations, and you can also do this yourself. Basically, this means that there is a force acting on both atoms together. Now, what is happening outside, near, inside the? I am just rubbing this part. Okay, so let me rub this part and show you. So if this is near the core, this is your star, spherical star. Okay, so photons are coming from inside. The mass of the star is very high. Okay, now these photons, they are interacting with what? They are interacting with basically near the surface. Okay, so they are interacting with atoms. Right. Now let me say that this is just basically hydrogen is there. So what will it interact with? It will basically interact with proton and electron. Okay, so these photons will interact with the hydrogen atom, which is basically proton and electron. Now, are the mass of proton and electron same? No, they are very different. Mass of electron is 18436 times lower, right? So this means that on whom gravity will work more, proton or electron? Proton. So gravity will work more on proton. So proton will be, so if I show you the bigger part, so proton will be here, on which the gravitational force will work. The gravitational force on electron is much lower. But these photons, they will interact mainly by electrons scattering with the electrons, and they will transfer their momentum to these electrons. Basically Thomson scattering process, right? So what is happening is that they are now getting all the momentum being transferred by this photon, and so they are pushing outward. They are getting the momentum in this direction, so they will move in this direction, right? So electrons are moving toward this direction, while Eddington, while protons are moving inwards because of the effect of gravity. Okay, but remember, this is an atomic system as a whole, bound by the electromagnetic interaction, right? So this means you cannot disrupt it together. So this means that the two forces, they will be acting together, and Eddington luminosity means when they are just equal to each other. This you can estimate also for this atomic system. So basically what we will have to do, we will have to match the gravitational force due to this proton with the force work transferred to this electron due to radiation, right? Radiation pressure. And if you match them together, you can check yourself that you will get a similar type of expression, where instead of this m as a function of r, you will get mp, mass of proton. You can get something like that.
মানে তখন যেন হাইড্রোস্ট্যাটিক ইকুইলিব্রিয়ামের ব্যাপারটা থাকে।
হ্যাঁ, ওটা তো আছে, থাকবে, সব সময় আছে। নড়ে যেটা ব্রেক করে দিত। এবার দেখো কি হবে। So this thing will be there. Now suppose the photons, the mass is very large. So what will happen? The photons will keep on giving energy to these electrons, right? But the force due to this gravitation, it is fixed. But this keeps on increasing. So what will happen is that the photon will be moved to a larger distance. The electron will be moved to a larger distance. So this means that inside the entire star, you can think of these scenarios like this. That means proton, electron. So this means that there will be an electric field, right? Because of the separation of the charges, positive inside, negative outside. There will be a separation of charges. There will be a sort of electric field will be there. Now, but still, if the radiation pressure is very large, then what will happen is that after some time, both will be pushed outward because the system will not break. Suppose I am assuming that the photon energy is not there, it will be ionized. System will not break. Then both will be pushed outwards. And this is how you can explain the disruption of the stellar atmosphere or stellar wind. বুঝতে পারছো, আমি একদম মাইক্রোস্কোপিক পিকচার হিসেবে তোমাদেরকে বোঝাচ্ছি যে মানে as a student of physics we sometimes talk about how things go, scaling relations, take for example, all that stuff, but this is a microscopic picture how things work, and in this way you can get the Eddington luminosity, right, like that. এবার দেখো, suppose this is a star, evolved star, where only helium is there. Only helium is there. Then what will happen? If this is an evolved star where helium is there, then just like this case, here we will have a alpha particle, right? And here only 2 electrons. Alpha particle, only 2 electrons. So this time you see the force is acting only on the 2 electrons, radiation force. Kintu gravitation force is acting on alpha particle, and the mass of alpha particle is 4 times that of the proton. এর মানে this time the Eddington luminosity will have to be 4 times higher. বুঝতে পারছো? এইটাই বলছিলাম যে this whole thing will depend. So how much luminosity will be the maximum that radiation can carry in a star in equilibrium will depend on the composition of the star. এটা আমি ইকুয়েশনের মাধ্যমে বলতে পারছি না, কিন্তু এটা আমি ইন্ট্রিনসিক থ্রু ডায়াগ্রামস, থ্রু দিস মাইক্রোস্কোপিক থিং, বুঝতে পারছো তো? সো ইফ আই আস্ক ইউ ইন দ্য এক্সামিনেশন, এক্সপ্লেন হাউ দি Eddington luminosity depends on the composition of a star. Understand? So this is how you can explain. You take hydrogen and helium as an example. So if you have a carbon atom, বুঝতেই পারছো how things will go. It will become even more difficult. Okay, so this is just talking about the microscopic picture. Now come back over here. So this is where we were, right? Eddington luminosity. Now at the surface, I can write it as small m is equal to capital M, total mass of the star. ঠিক আছে? At the surface, total mass. তাহলে এইটাকে অনেক সময় ক্যাপিটাল এ, দেখো এটা স্মল এ আছে, and that is capital M. Sometimes it is also written like that. So this is the total Eddington luminosity at the surface, total luminosity output. But this one is just at the inside part. Okay. Now this thing, if I put in the various constants, I can write it like this over here. This form. Here I have, you see, written in terms of m by m solar, kappa due to electron scattering divided by the total kappa into solar luminosity. But remember, this Eddington luminosity is proportional to mass, m to the power 1. Now where have you seen this thing? You remember this thing that I previously talked about? So this is your theoretician's HR diagram. Fine. So this is my HR diagram, and here this is the main sequence part. Okay. Again in this main sequence part, you see this is low mass, intermediate mass, high mass. Low mass, it is observed experimentally that luminosity scale says m to the power 5, intermediate mass m to the power 3, and high mass m to the power 1. So this means that you see it is finished. Over here it doesn't extend. So this means that there is a limit above which you cannot go below. Something like that. And that limit is basically this Eddington luminosity. So when these two matches, after that you cannot have a star, because if you keep on giving the mass to the star, the upper surface will keep on blowing away. বুঝতে পারছো? Now let us do an estimate of the maximum limit of the maximum mass of a star using this. So let me take as an approximation. Suppose L is of the order of m to the power 3.5. I am giving an equal sign over here. And now I am using the solar values. Then I can write as L Eddington equal to 3.2 into 10 to the power 4 into m max. Now if I equate these two, then you can get, you see, m max, a rough value of around 64 solar masses. So you can still get a value estimate of how to calculate the upper mass. So we are having two very different techniques, one over here, one another here. ঠিক আছে? বলো, any question? And microscopic picture is very interesting.
Sir, এই জায়গাটা স্যার আরেকবার বলতে পারি।
কোনটা বলো?
স্যার এই ভ্যালু বসিয়ে
আমি দেখো এখানে এই ভ্যালুসটা তো নিয়েছিলাম, এখানে আমি যদি সোলার ভ্যালুস নিই তাহলে আমার দেখবে এইরকম অ্যাপ্রক্সিমেশন অনেক জায়গায় করি। পার্টিকেল ফিজিক্সে c is equal to h plus is equal to 1 ইউনিটস, ন্যাচারাল ইউনিটস নিই, এখানে আমি সোলার ভ্যালুসের টার্মসে এটাকে লিখেছি। ওকে, লিখে আমি জাস্ট তোমাকে একটা অ্যাপ্রক্সিমেট ভ্যালু বলছি, ইউ ক্যান গেট সামথিং লাইক দ্যাট। Any questions? Any more?